So now we're going to look at another application of the ideal gas equation, and we can use it to derive an equation for determining the density of a gas, all right? Now, please note that gas densities are not used in the same way as we would use densities for solids and liquids, right? We tend to use the densities of solids and liquids as a particular useful physical property because basically the densities of solids and liquids do not change much upon any change in temperature or pressure. The same is not true for gases, of course. Gases change fundamentally and very dramatically, especially with respect to their volumes, when, for example, the temperature decreases or increases, and therefore that can affect the density of the gas, all right? Another thing I want to say here is that typically gases are much less dense than liquids and solids, and therefore typically their densities are expressed in grams per liter. All right, now, if you remember, we talked about this equation, which is used to determine the molar mass of a gas. We can actually rearrange it to get an expression of m over v equals to everything else, because m over v by definition is a density, mass over volume. So when we rearrange it that way, we're going to get this expression. M over v, and that is lowercase m over v, would be equal to the molar mass times the pressure divided by r times t, right? So basically, since the density is equal to m over v, we can replace m over v with d, which is the density, which is equal to mp over rt, all right? So basically, if you know the molar mass, if you know the pressure, if you know the temperature of the gas, then you can determine the density of the gas. And based on this equation here, we can find out that there are some relationships between the density of a gas and two important functions, or two important variables, I should say, the pressure and the temperature. So basically, everything else being the same, the pressure of the gas, if it increases, will increase the density. So there's a direct linear relationship between the pressure of a gas and the density. And then down here, we have a relationship between the density and the temperature. So again, everything else being the same, basically there's an inverse relationship between the temperature and the density. So therefore, as the temperature increases, the density decreases, and vice versa, all right? And in fact, another thing I should mention here is the molar mass, right? You can compare the densities of different gases simply based on the molar masses, again, provided that everything else is the same. So if the pressure and the temperature are the same, then if you compare two gases, the one with the heavier or the larger molar mass would be the one with the greater density. So those are just some relationships that one can establish based on this equation between the density on one side and either the molar mass, the pressure, or the temperature, all right? Okay, so let's look at a problem where we can apply this equation. So this question, they gave you the density. Let me change the ink color on this. I prefer the black color. Okay. So in this particular question, they gave you the density. They gave you the formula of the gas. They gave you the temperature in Celsius and the pressure. Now remember, the equation is density is equal to mp over RT. So the question is asking for you to calculate the density. So all we have to do is put the numbers in. Now the first thing we need to determine is the molar mass of methane. So for the molar mass of methane, let me do a quick calculation. I think it is 16.04, but let me, so 4 times 1.008 plus 12.01. I was right, 16.04 grams per mole. So 16.04 grams per mole would be the density of methane multiplied by the pressure, which is 0.978 atmospheres, and then divide that by R, which is always going to be 0.0821 liters atmospheres over mole Kelvin. Can't forget all those units. And then we multiply that by the temperature in Kelvin. Now they gave you the temperature as 25 degrees. So when we add 273 to that, that becomes 298 Kelvin. All right. And again, some units will cancel out. The mole will cancel out. What else? The kelvins will cancel out here and here. The atmospheres will cancel out here and here. And we end up with the final units left, which would be the grams divided by liters. So whatever the answer you're going to end up with, that would be expressed in grams per liter. So what we need to do now is the number crunching. So we're going to have 16.04 times 0.978 divided by 0.0821 times 298. And according to my calculations, whoa, this can't be right. Let me do this again. 16.04 times 0.978 divided by 0.0821, 298. Okay, so the answer I got here is, I don't know why this answer looks funny to me, but anyway. The answer I got here is 0.641, rounded off to 3 sig figs, grams per liter, all right? Okay, so that's basically how we do this example. All right, let me move on to the next example here. Now, this one is a bit different because it's asking for the pressure. The question says, what must the pressure of oxygen be maintained at 25 degrees Celsius to have a density of 1.5 grams per liter? So we're going to use the same equation. Density is equal to PM divided by RT. But what the question is asking for is P. So we could rearrange this equation to get P equals to D RT over M. And then all we have to do from here is plug the numbers in. So the density is given as 1.50 grams per liter times R, which is 0.0821 liters atmospheres over mole Kelvin. Excuse me, times the temperature, which is 25 degrees, which would be equal to 298 Kelvin. And then all divided by the molar mass, which for oxygen is 2 times 16. So therefore, that would be equal to 32.00 grams per mole. And again, we have to do some unit cancellations, as you can see here. The moles will cancel out here. The Kelvin will cancel out here. And what else? The liters will cancel out here. So the only unit remaining will be the atmosphere unit. All right? So down here, I'm going to say the answer will be expressed in atmospheres. And we're going to do the calculation, 1.50 times 0.0821 times 298 divided by 32. And according to my answer, it's going to be okay, we have to run this off to 3 sig figs, so 1.15 atmospheres. Okay, so that's basically how that is done, all right? Okay, so I'm going to stop this video here, and the next video we'll be looking at, well, to begin with, gas reaction stoichiometry. So we're going to look at the principles of stoichiometry that we learned in earlier chapters and apply it to gaseous reactions. And you're going to see that we're going to combine a lot of things that we learned with respect to the gas laws and what we learned about stoichiometry earlier. So that's for the next video. Until next time.